square, and some important patterns in square numbers. Adding odd numbers, a sum of consecutive natural numbers, product of two consecutive even or odd natural numbers, finding the square of a number, Pythagorean triplets. Adding odd numbers. Let us see what happens when successive odd numbers are added. Consider the following. Addition of first odd number, that is 1, is 1, that is 1 square. Sum of first two odd numbers, that is 1 plus 3 is 4, that is 2 square. Sum of first three odd numbers, that is 1 plus 3 plus 5, that is 9, which gives 3 square, and so on. So, we can say that the sum of the first and odd natural numbers is n square. In another way, we can say that if the number is square number, it has to be the sum of successive odd numbers starting from 1. 25 is a perfect square. How? We have a number 25. Now we have to prove 25 is a perfect square. For this, we subtract 1, 3, 5, 7, 9 successively from 25. We get 25 minus 1, 24. 24 minus 3, 21. 21 minus 5, 16. 16 minus 7, 9. 9 minus 9, 0. This means 25 is equal to 1 plus 3 plus 5 plus 7 plus 9. So we have proved 25 is a perfect square. Is 38 a perfect square? Find it. Now we have to find 38 is a perfect square or not. Again we do as above. We get 38 minus 1, 37. 37 minus 3, 34. 34 minus 5, 29. 29 minus 7, 22. 22 minus 9, 13. 13 minus 11, 2. 2 minus 13, minus 11. This shows that 38 is not a sum of successive odd numbers starting from 1. Hence, 38 is not a perfect square. A sum of consecutive natural numbers. To study this property, consider these examples. 3 square is equal to 9, 4 plus 5. 5 square is equal to 25, 12 plus 13. 7 square is equal to 49, 24 plus 25. Now, if we observe first example, 3 square, that is 9, is a sum of successive natural numbers, 4 and 5. We get 4 as 3 square minus 1. We get 4 as 3 square minus 1 by 2 and 5 as 3 square plus 1 by 2. Similar way, we get 12 and 13 for 5 square and so on. Product of two consecutive even or odd natural numbers. Suppose 11 and 13 are two consecutive odd natural numbers. Therefore, 11 multiplied by 13 is equal to 143. We can write 12 minus 1 instead of 11 and 12 plus 1 instead of 13. Therefore, 11 multiplied by 13 is equal to 12 minus 1 multiplied by 12 plus 1, which gives 12 square minus 1. Since a minus b, a plus b is equal to a square minus 1. 12 square is 144 minus 1, which gives 143. Similarly, 13 multiplied by 15, 14 minus 1 multiplied by 14 plus 1, which gives 14 square minus 1. That is equal to 255. 29 multiplied by 31 is equal to 30 minus 1 multiplied by 30 plus 1, which gives 30 square minus 1, 899. In this property, the product of two consecutive even or odd natural numbers, that is, a minus 1, a plus 1, is equal to a square minus 1. Some more patterns in square numbers. Observe the squares of numbers 1, 11, 111, and so on, etc. They give a beautiful pattern. Another interesting pattern. Finding the square of a number. We can easily find squares of small numbers like 3, 4, 5, 6, 7, and so on. But can we find the square of 23 so quickly? The answer is not so easy, and we may need to multiply 23 by 23. There is a way to find this without having to multiply 23 multiplied by 23. We know 23 is equal to 20 plus 3. Therefore, 23 square is equal to 20 plus 3 the whole square. Multiply 20 of first bracket with second bracket and then 3 of first bracket with the second bracket. We get 20 multiplied by 20 plus 3 multiplied by 20 plus 3. 20 into 20 is 20 square plus 20 multiplied by 3 is equal to 60 plus 3 multiplied by 20 is equal to 60 plus 3 square is equal to 9. That is 400 plus 60 plus 9, which gives 529. Other patterns in squares. Consider the following pattern. 25 square is equal to 625. That is 2 into 3 hundreds plus 25, which gives 2 into 3 is 6 into 100 plus 25, which gives 6 into 100 is 600 plus 25, giving 625. Similar are the given patterns. Pythagorean triplets. To understand Pythagorean triplets, let us consider the following example. 3 square plus 4 square is equal to 9 plus 16, which gives 25, that is 5 square. Can we write it as 2 square minus 1 the whole square plus 2 into 2 the whole square is equal to bracket 2 square plus 1 the whole square. Now compare this equation with 2m the whole square plus m square minus 1 the whole square. It gives m square plus 1 the whole square. The value for m in the first equation is 2. Therefore, the collection of numbers 3, 4 and 5 is known as Pythagorean triplet. For any natural number m greater than 1, we have 2m the whole square plus m square minus 1 the whole square, which gives m square plus 1 the whole square. So, 2m, m square minus 1, m square plus 1 forms a Pythagorean triplet. Find 6, 8, 10 is a Pythagorean triplet or not. Since 6 square plus 8 square is equal to 36 plus 64, which gives 100. It is 10 square. Here we can write it as 2 into 3 the whole square plus 3 square minus 1 the whole square, which gives 3 square plus 1 the whole square. Now compare this equation with 2m square plus m square minus 1 the whole square. It gives m square plus 1 the whole square. The value for m in first equation is 3. Therefore, the collection of numbers 6, 8 and 10 is the Pythagorean triplet. That is all in this topic, students. Let us learn about square root, finding square root through repeated subtraction, prime factorization and division method, square roots of decimals in our next topic. Keep learning.